Welcome to Curiosity Cake, the podcast about ideas for people with curious minds and big appetites. I'm Lee Delaney. I've made it my mission to bring you a feast of ideas across science, technology, humanities, society and culture, and more. Each episode, I'll be talking to an expert from academia or industry to find out about their work and what we can learn from it. If you like what you hear, please tip generously by leaving a review on your podcast platform of choice. Reviews are really important for getting the podcast noticed. On this episode, I'm getting schooled on nuclear fusion by plasma physicist Nick Walkden. Nick has spent his career at the Culham Centre for Fusion Energy, part of the UK Atomic Energy Authority. Culham's mission is to develop sustainable fusion energy, and as you'll hear from the interview, they're at the very cutting edge of fusion. Now get yourself a cup of tea, grab a fork, and dig into a slice of curiosity cake. Curiosity Cake. Nick, welcome to Curiosity Cake.
Thanks, Lee. Nice to be here.
It's really good to have you, and particularly because I think you have this really amazing job title of Plasma Physicist. So I'm really interested in what that is and how you came about becoming a plasma physicist.
Yeah, you don't see that one too often, do you? I used to tell people I was a nuclear physicist because no one knew what a plasma physicist was, and I always thought nuclear physicist sounded more interesting. But it's so. I guess how to describe a plasma physicist? Plasma physicists, we deal with things that are very hot gases to do very cool stuff. So there are lots of plasma physicists. My particular indulgence in plasma physics is in fusion and fusion energy, which is taking things, making them very hot and trying to understand how they work. Plasma is the fourth state of matter. It's and I think it always does. I mean, obviously I'm biased, but I think it does it a disservice by calling it the fourth state of matter. So many people, most people, at least certainly some of your listeners won't have heard of plasma or well, let me take a step back. When I was in university, I did a physics degree in university. I didn't know anything about plasmas until I started studying them for my PhD. So they're really things that aren't taught, and the reason they're not taught is because they're just phenomenally complex and hard to understand. And I think a lot of people, when they hear the word plasma, think to like Ghostbusters or like Iron Man, his plasma jets, or Batman, or things like this, or Star Trek. But there's some vague connection there. I mean, in Ghostbusters, for example, we probably all remember the proton pack. That is probably a plasma. But what plasmas actually are, so you take, let's take some ice. You take some ice. That's a solid, right? All of the atoms in that are tightly bound together. They're jiggling around, but they're tightly bound together. You heat that ice up and you get water. Water is a liquid. So all the atoms in the liquid are slightly less bound to each other. So the hot thing as a whole has slightly less form, but it's still sort of held in the same volume, right? The classic thing is solids hold their shape, liquids hold their volume. Heat the liquid up a bit more, you get steam, and steam is a gas, and gases sort of fill whatever volume they're in because they're just individual atoms that can move around. So let's take that another logical step now. Let's take that to its kind of logical conclusion. If I take that gas and I heat that gas, if I superheat that gas, well, we remember that atoms are actually these nuclei, these positively charged cores with electrons orbiting around them, a bit like a moon orbiting a planet. And so if I heat those, what's eventually going to happen is that moon, that electron, is going to orbit super, super fast. Eventually it's going to break free. And that's what a plasma is. So a plasma is just like a gas, except all of the electrons and all of the positive ions, the cores of the atoms, are moving around independently, which it sounds quite logical when you put it in that kind of order. So yeah, plasma is the fourth state of matter, but actually something like 97 or 99% of all of the matter in the known universe is in the plasma state. Because you look up in the sky, every single star you see is a big burning ball of plasma. It just so happens that where we are down here on Earth, the conditions are not very conducive to plasma formation, which is pretty lucky for us because they're not a particularly nice place for our soft, squishy bodies to be.
Except for when it comes to fusion and trying to get that superheat going that you were mentioning.
Except for when it comes to fusion, exactly. Yeah.
Yeah, so we can come back to that one. But can you say a bit more just about your career up to this point, your early
Yeah.
days studying?
Absolutely, yeah. I would love to be able to tell you that I wanted to be a fusion physicist and solve the world's energy problems from when I was like 2 years old. But actually, I up until about 16, I wanted to be a greasy metal guitarist. I wanted to be a vet. I wanted to be a language student. I took physics at university because I thought physics was something really interested me. All through university, I wanted to study string theory because what physicist doesn't want to study string theory?
And particularly a heavy metal loving physicist.
Exactly, heavy metal loving string theorist. I mean, could I be more cliche? But in my in university, I was lucky enough to get to do a placement at the UK Atomic Energy Authority, and and this is where I work now. So I did my placement there. I learned all about fusion and what fusion is and what it does and what it's working towards, and it's just, I mean, so the physics that we do is really, really interesting. There is so much in plasma physics that you just blows your mind. But what I love about it is that whilst you're doing that, everything you're doing is working towards this goal, which is to provide an energy source which can fuel us for millions of years safely and carbon free. So it's just a wonderful thing to work on because you have this really interesting stuff you're doing, but at the end you've got this golden goal that you're aiming for. And yeah, that so I did my placement at UK Atomic Energy Authority, Culham. The lab in South Oxfordshire is called Culham. Went on, did a PhD, and I've been there ever since. Really, I'm kind of the poster boy for Culham.
You spent most of your time there, which is probably reasonably unusual now with lots of people switching careers, switching companies and things.
Exactly, yeah. I mean, there's not many people that do fusion. Although fusion is quite an international thing now, and we've got more and more private companies shooting up. Since I began my fusion career, there's at least I can think of at least 3 or 4 examples of private fusion companies that have shot up and are now, taking in a lot of money to develop their own products. So it's a really expanding field, and once you get in there, you kind of get hooked. It's such an exciting place to work that you just kind of get hooked. And we really are the lab. Obviously, I'm very biased towards this, but the lab we work at, it really is sort of a world leading facility. It might not look it when you get there because a lot of the buildings are sort of 1960s concrete, but it really is a world leading facility. And once you start working at a place like that, it's very, very hard to want to move off and do something else. And I love it. I think it's a wonderful place to work, and it's just so interesting every day.
Is it an area then where there's a lot of competition for jobs, something that's difficult to get into?
In a lot of science areas, job competition is pretty hard, especially if you go through the academic route, right? Lots of PhDs struggle to stay on the academic ladder, and lots of PhDs don't want to. In fusion and fusion physics and fusion engineering, there's such a rapid expansion at the moment that actually the job market is quite open. We're always searching for sort of the top talent to come and work on these sort of things. So it's a real burgeoning field. Yeah. There's a lot of stuff opening up now.
Now's the time to get in if you're interested in it.
Absolutely, yeah. Now's the time to jump in, and it's a really exciting next couple of decades that we've got coming in the fusion field as well.
Yeah, it sounds really exciting. Again, one of the reasons why I wanted to do this particular episode. So if we get into then what fusion actually is and why it's significant.
Yeah, absolutely. Sorry, I've said fusion about 10 times and I haven't really told anyone what it is yet. It's before I go into that, we've got this great habit in fusion of doing 2 things. One is just assuming that everybody knows how awesome and how exciting fusion is. And the second is we have just hundreds and hundreds of acronyms. So if I say an acronym during this interview and I don't explain what it is, please, Lee, pull me up on it because we have so many.
Will do.
And I do it in my sleep. Yeah.
Very used to that in my day job.
Absolutely. So what is fusion? The best way to describe fusion is to not talk about fusion first. So you've probably all heard about nuclear power. Everyone is kind of familiar with nuclear power. So nuclear power is this process called fission, where you take a big atom, something like uranium or something, and you split it in 2. And Einstein tells us that energy, or at least change in change in energy is the same as a change in mass. E equals mc squared. So you split something in two, and it turns out that in fission, when you split something heavy in two, it turns out that the two things you're left with are very slightly lighter than when they were the whole at the start, and that change in mass can create energy, and that energy is what you harvest. Fusion is, in many ways, the exact opposite. So you're taking two very, very light elements, so like hydrogen or something around hydrogen, which is the first element in the periodic table, and you squish them together, and they can bond together. There's something called a strong nuclear force, can take hold and bond them together. And it turns out that when they're bonded together, the weight, their mass, is very, very slightly lighter than when they were separate. And again, because you're now losing mass, you're gaining energy. And it turns out that in equals mc squared, that c, the c squared, is the speed of light. And the speed of light is very, very fast. So you square it, you get a very, very big number. So you don't need to change mass very much to harvest an enormous amount of energy. And it's that energy that we try and harvest in fusion. It's exactly the same process that goes on in the middle of the sun. So in the middle of the sun, you have protons, you have hydrogen fusing, and that is at the core what drives the sun. It's exactly the same process, but we just want to harness that here on Earth to harness that amazing potential in the energy source.
So how do we go about harnessing that here on Earth?
Oh, with great difficulty. How do we do it? Well, first thing to say is that the sun is not a good fusion reactor. The way that the sun does fusion, it fuses protons, hydrogen and hydrogen. It's extraordinarily inefficient, which is really good, right? If it was any more efficient, we wouldn't be here, and the sun would have burnt out billions and millions of years ago. So good news that the sun is an inefficient fusion reactor, but bad news if you want to try and get fusion to run on Earth. So we don't use hydrogen. What we actually use is something called deuterium. You might know it as heavy water. Have you heard of heavy water? So heavy water is one proton and one neutron. And double heavy water, heavy hydrogen, not heavy water. Double heavy hydrogen is tritium, which is one proton and two neutrons. And it turns out that when you take deuterium and tritium and you try and smush them together, they are the most likely combination to fuse of any combination of atoms that we know of. So they're the best option we have. And it means that we can fuse them at lower temperatures. And when I say lower temperatures, I mean the chilly temperature of 150 million degrees. So our challenge is to take some deuterium and some tritium, heat them up to 150 million degrees, get them to fuse, and then harness the energy that comes out the other side. And the energy comes out in two forms. So we get a helium nucleus, which is two protons, two neutrons. And if you do the maths, so we've got on the left-hand side, on the deuterium and tritium, we've got one proton and three neutrons. On the right-hand side, we've got helium, which is two protons, two neutrons. So we've got one neutron left over. That neutron flies out, and it's the energy in that neutron that we're going to harness. And we're going to use that to drive, I don't know, something like a steam turbine on the outside of the machine, create steam, create electricity that way. So it sounds, it doesn't sound easy, but it sounds doable. It is doable. The challenge is keeping all of the fuel there, because it turns out, probably unsurprisingly, that when you heat something to 150 million degrees, it doesn't like to stay there for a very long time. So the challenge is to do that safely and in a controlled manner so that we can keep the process going. Essentially, we can keep logs on the fire and we can keep the process going. And that's how we try and do fusion on Earth. Now, there are a fair few different ways of doing that, but at the core, that is what we're trying to do.
And 150 million degrees just seems really hard to understand how hot that actually is.
It's mind-boggling, isn't it, right? So the core of the sun is 15 million degrees, and that's pretty hot. 150 million degrees is just staggering. When we have a machine in South Oxfordshire called JET, which is the Joint European Torus, and when JET is running, it is, for most of the time it's running, it's the hottest place in the solar system. And, that is just quite a staggering feat. And actually, there's an even better stat than that, because if you think about the size of the sun, so the sun is 15 million degrees at its core, goes down to about 5,000 degrees on its surface. But the amount of space it needs to do that is, millions and millions of miles, many, many times the Earth's diameter. So it takes a huge distance to get from that hot to that cold. What we're trying to do in our machines is take something to 150 million degrees and then reduce it to room temperature in the space of about 3 or 4 meters. And that difference in temperature sustained is probably the biggest difference in temperature that we know about, probably in the known universe. So in doing fusion on Earth, it's not just a case of heating stuff up really hot. It's a case of essentially bending the laws of nature in a way that they do not want to be bent, so that we can get all these things to stay still and do fusion. And it's, that's the challenge. But we do it, right? We do it all the time in South Oxfordshire, all around, in other places around the world. We do fusion.
So how has fusion developed over time, coming up to what you're able to do at the minute?
Oh, that's a great question. So we learned about fusion back in the 1920s. Sir Arthur Stanley Eddington, really, really famous British physicist, polymath. He was the first person to postulate that fusion powered the sun. After he did that in the 1930s, people were actually thought about it a bit more, figured out exactly what sort of fusion was going on in the sun, and started to be able to create fusion in a lab just by firing really high energy beams of particles at other targets. They could do really isolated fusion events in labs. So people started to learn about it. And then we had the war. Then we had World War II. And weapons programs built up. And the first idea of controlling fusion in a sort of sustained controlled manner really came out of all these weapons programs. Fortunately for us, it very quickly became obvious that controlled fusion had absolutely no weapons application. It was entirely useless for weapons application. And that's where fusion research for peaceful means, for energy production, really started to kick out from. And there's a really interesting history that takes us from then to now. I will give you just the very potted version of it because it's a long and interesting one. But basically, right now, we have lots of different concepts for fusion. We have the one that we work on, which is called the Tokamak, which is, we think, the most promising route to fusion and widely acknowledged as being the closest route to fusion. But there are a number that are around the place. They all really had their genesis in the 1950s and 60s. And a lot of this was kicked off in Argentina, where there was this project called Project Humel, which the Argentinians released a press statement saying, "We've done it. We've delivered fusion energy. We've produced as much energy out as we were putting in." And that press statement could have sent cascades around the world. And all of a sudden, you started having programs in the US, in the UK, in Russia, all around the world starting to pop up and really get their funding to generate these ideas. And that's where all of these different concepts started to be designed from. It turned out that actually the Argentinian scientist who was proposing or produced these results was a fraud and was later arrested for fraud. They never got fusion to work, but what that press statement did do is really catalyze all of the different ways that we can do fusion now. And you cycle on 50, 70 years, and we've got this burgeoning world of fusion where we've got the Tokamak at the center as our mainstay device, the one that we think is closest to fusion. But you also have all of these other different concepts around the edges, which are sort of higher risk, more requiring more innovation, more development, but are also coming up with really interesting ideas on how to do it.
That's brilliant. So it's really came from someone who was actually just making stuff up in some way.
Yeah, someone who wanted a quick buck, making stuff up, getting his funding, and actually sort of triggered the genesis of all of the real funding injections that fusion needed to start getting it off the ground.
And in terms of the benefits and the potential of fusion, like, it just sounds like it's almost unlimited in some way.
Yeah, it's one of those ones that almost sounds too good to be true. The benefits of fusion, there are a few. So the process that I spoke about, where you have deuterium, tritium making helium and a neutron, one thing you'll notice is there is no carbon in that. So it's a completely carbon-free way of generating energy. Not only that, but it is the highest yielding energy reaction that we have. So it yields more energy than nuclear fission does, far more energy than any of the combustion type energy production methods, so carbon, oil, natural gas, and far more than any renewable type. So it's a really, really high yield energy source. But what's beautiful about it is that it's also really, really abundant. So if you have a glass of water and you take a sip of that glass of water, or a glass of seawater, about 1 in every 6,000 hydrogen atoms in that seawater is actually deuterium. So deuterium we have in abundance, right? We do not need to worry about deuterium. Tritium, on the other hand, is a bit more difficult. So tritium is radioactive. It has just over a 12-year half-life, which means that if I have a tank of tritium and I leave it for 12 years, I come back and I only have half of my tank remaining just because of radioactive decay, which is a pain. So you can already imagine all of the difficulties that there are in keeping hold of it, handling it, and storing it. That's not the half of it, though. It also doesn't form naturally because, well, why would it? If it's got 12-year half-life, why would it form in nature? At the moment, it's really the main place that we get our tritium from is in nuclear fission reactors. CANDU reactors in Canada are the main supply of tritium in the world. So, but even then, even all of the tritium we have in the world at the moment could probably start up one fusion power plant, and that would be it. So a fusion power plant will have to be self-sustaining. It will have to create its own tritium. And the way that it's going to do that is around the outside of the thing, you have a bed of lithium or some material with lithium in it. Because when you take lithium and you bombard lithium with neutrons, it produces tritium. So we have this process now. We have the cycle. Excuse me. We have this cycle where we produce neutrons. Neutrons is the one thing that we do not have an issue with. We can produce neutrons, fire those neutrons into a blanket of lithium, and we can create our own tritium. So we can then pump that tritium back in, do the fusion, create the neutrons, create more tritium, pump that tritium back in. So we have a closed tritium cycle. And that's how we're going to do it. And it means that actually our fuel source is deuterium and lithium. And lithium, at the moment, there's about a few thousand years of supply of lithium, but there are new mining methods being developed, particularly getting lithium from seawater in the seabed. And once these are fully developed, we expect there to be enough fuel on Earth to run nuclear fusion reactors for the whole of the Earth's supply for millions of years. So it really is absolutely abundant. To put it into context for you, if you took a bath of seawater, and I'm talking to you on a laptop at the moment, and I imagine you're talking to me from a laptop or a desktop. If you take the battery in our laptops, all of the lithium in that battery, you've got enough potential for energy production in that fuel that it could power our houses for about 60 years. So the energy abundancy is massive. And it's a really interesting thought because at the moment, our energy is really dependent on supply. What happens if supply is no longer the issue? Well, then our energy starts to become on availability of knowledge and availability of the plants. And it's a really interesting thing to start thinking about the dynamics that can start to bring in. But yeah, so fusion it sounds too good to be true. It's not too good to be true. All of these things are there, and it's safe as well. It's inherently safe. The problem is that it's just so challenging to get right. I've already told you that we're trying to bend the laws of nature out of their natural habitat, right? We're trying to bend them away from where they want to be. And obviously nature doesn't like to do that, and nature fights back. And it's really controlling that, bending these laws of nature out of their natural inclination that we have to contest with. And that's what makes fusion so incredibly hard.
Yeah, it has the potential to be such a game changer in terms of energy for all sorts of different reasons, really. The amount of energy, the length of time, but also, those political issues around energy, like energy security.
Exactly, yeah. Energy security is a big one, and energy availability. So you think where if you want to decarbonize, we should all want to decarbonize, right? We should all be viewing an energy economy after 2050 where there is no carbon. Now, we could probably do that in the UK. We have the kind of natural resources to do that based on renewables, although it would require just a phenomenal investment in our energy infrastructure. But we could probably do that. But you look at really population dense areas like India, China, other areas, and who don't really have the access to coastlines or the ability to put up solar panels all over the place. And you think, how on earth do you decarbonize that energy supply? Well, what you need is you need an energy supply which is incredibly energy dense, which means that it doesn't take up much space, but it can produce a huge amount of energy. And that is exactly what fusion can give you. It's this really energy dense production method. So it kind of fills a gap that the only other real way of filling that gap is through nuclear. And I'm really pro nuclear, right? I'm not going to come out here and try and bash nuclear power. But the problem with nuclear is it's not well, one of the problems with nuclear is that it's not particularly politically desirable because of all of the weapons connotations that come along with it. And also the fuel sources aren't massively more abundant than fossil fuel sources are anyway. So even if you didn't care about the carbon imperative, just energy security in general, nuclear fission doesn't actually give you dramatically more energy security necessarily than other supplies. So fusion can really sit in that space. Of course, the problem with fusion is getting there, because people have been talking about this for years and years, and we're still somewhere away from being able to produce fusion power plants to put energy on the grid. But that's the sort of space that fusion energy can occupy. And the other thing is it's base load. So you can run fusion at night. You can run fusion on non-windy days or when the tides are out. So fusion is base load. You can just turn on and off these plants. So it can really fill a gap in a post-carbon energy economy that I think is kind of hard to fill at the moment.
But it sounds like there's maybe a bit of public relations work to do for fusion there.
I mean, I think the biggest public relations work we need to do for fusion is to tell people about fusion, because it's remarkable how few people really understand what fusion is and why we do it and why it's so exciting and so amazing. And I really hope that in the next few years, with all the excitement that we've got going on in the field, that changes, because it's a really exciting, really amazing thing to be part of.
Hopefully this podcast can be a part of introducing it to people and changing their minds.
Absolutely. Everyone who's listening, go and tell your friends all about, extol the virtues of fusion wherever you go.
So you're talking there about where we're at currently with fusion and where it needs to get to. So you talked a bit about the history. So where are we now with fusion? What can we do?
We can do a lot. So where are we now? We have, I think at last count, there is something like 60 to 70 fusion devices around the world. Not all of them do fusion. Most of them don't actually do deuterium-tritium fusion, but they all are experimental devices, working towards doing fusion. The biggest and the best in the world is JET, which sits at our lab in South Oxfordshire. And I'm not saying that as someone that works on JET and does experiments on JET. I'm saying you can say that completely objectively, because JET holds the world record for the amount of fusion produced. So JET in 1997 produced 16 megawatts of fusion power, which is substantial, right? That's not a small amount of power to produce. Unfortunately, that was only about 67 or 68% of all of the power that it took to create it. So we've never yet got to that point of creating more power out than we put in. But we've got to the point where we know we can do fusion reliably and we can produce a lot of power. I was about to say easily, and I think a lot of people would tell me off if I said easily. It's certainly not easy to produce that amount of power, but we've got to the point where we can do it, I would say, semi-reliably when we need to. The next stage is proving that you can get more power out than you can put in, because that's really the cornerstone. Once you can do that, you go from what is essentially a series of experiments up to delivering fusion in a commercial capacity. And that's what ITER is. So ITER is this machine that's currently being built in the south of France. And the headline goal of ITER is to produce 10 times the power out that we put in. And ITER is a really special thing. So maybe I'll take a step back and I'll say, so JET is operated in the UK, but it's operated on behalf of the European communities. So we have an operating contract with the European Commission, and we operate the machine, and we have scientists from all over Europe come in and do their research on JET. ITER.
And JET and ETA are acronyms in themselves.
Sorry, yes, well done, Lee. You caught me. So JET is a joint European tourist. Yeah, that's. I knew I'd fall in that. Funnily enough, ITER. ITER used to be an acronym, but it actually changed. So ITER is no longer an acronym. ITER it means something. I don't think it means this exactly, but it essentially means the way in Latin, and that's the name of ITER. So I can't. I nearly caught myself out, but actually, thanks to a little change in public relations a few years ago, ITER is actually not an acronym. So JET is the Joint European Tourist, and it's this Europe-wide experiment. ITER is the next kind of logical progression from that. So ITER had its. So it really it had its genesis in a meeting between Gorbachev and Reagan in 1985 at the sort of tail end of the Cold War, where they decided to work together. They needed an announcement at the summits that they were talking at, and they decided that a good announcement would be that the US and USSR, who were both had major fusion development programs at the time, were going to come together and build this global device that was going to produce more power out than it put in. And that was kind of the genesis of ITER. Since then, other people have joined. So at the moment, ITER is a partnership of the US, Europe, China, India, Japan, South Korea, and Russia. 7, that's right, yep. Which is amazing, right? So 50% of all of the world's population has a representation in ITER, and 90% of all of the world's economy has a representation in ITER. So it's really a phenomenal thing. It's easily the most complicated science experiment ever built, and not just from a scientific point of view, but from an administrative point of view as well. If you can just imagine trying to build a program where China and the US and Russia are all kind of happy to work together in the same way. It's such a phenomenally complicated thing. But yeah, sorry, I diverge. So ITER is going to produce more power out than is put in, and it's being built in the south of France. It's due to start coming online around about 2025. So that's kind of where we are at the moment. We've had years and years of experiments, and all of these experiments have now taken us to the stage where we believe that we're kind of ready to start proving the principle, and that's what ITER is going to be. At the same time, there are other approaches to fusion. So in the US, there's a big push towards something called inertial confinement fusion, where you fire lasers at small cryogenically frozen targets of deuterium and tritium, and those lasers essentially crush the fuel, and right at the center you get a really hot spot, and that's where the fusion occurs, and that's where you start to do fusion. So that's a popular that's one of the methods that's being investigated in the US. And then there's a real rise in private sector fusion at the moment as well. So with all of these fusion concepts popping up in the US and the UK in private companies, and they're starting to attract really rather respectable private finances, private funders to come and fund these things. So we have this direction that we're on where we think we're going to get more power out than we put in, but also there are all of these sort of bubbles of interest and innovation that are shooting up as well. So it's a real burgeoning field at the moment.
And the Tokamak is the approach that you use at UK AEA, and that was actually a Russian invention?
Yes, yeah. Correct. Yeah. So the Tokamak is so first off, Tokamak is a Russian acronym, and I'm not going to try and pronounce what the word Tokamak stands for, but what it means is toroidal chamber with magnetic coils, and that is essentially what it is. So I said that you have to take this plasma and you have to heat this plasma up to 150 million degrees, and you have to keep it somewhere, because this thing wants to expand out and just get. The natural size of a fusion reactor is the sun. So we need to make sure that we don't let it expand out to the size of the sun, that we keep it somewhere. And the way you do that, or the way that we do that, is with magnetic fields. Really, really strong magnetic fields. We create a kind of cage with a magnetic field, and that cage is something that we can put the plasma in, keep it there, and superheat it. And that's what a tokamak is. And that cage in a tokamak is sort of donut shaped. So it's a torus for any of the mathematically inclined that are listening. And so we keep that magnetic cage in a torus, but we don't want that cage and that plasma just open to air, because air contains lots of nasty things like oxygen, hydrogen, nitrogen, things like that, which we don't want getting into our plasma. So we keep it in a vacuum. And that's essentially what a tokamak is. So it's a toroidal chamber with magnetic coils. So tokamaks have an interesting history because they came out of Russia. They were invented in Russia in the 1950s, whilst the rest of the world was fighting with all sorts of other concepts. There's a great quote from a former head of UK Atomic Energy Authority who said that in the old days, there was one boss and there were 7 different designs. There were 7 different machines. And all of these different machines were like, the different approaches that you have to fusion. Z pinches, toroidal field pinches, all sorts of different magnetic configurations to do fusion. Nowadays, there's one machine and there's 7 bosses, i.e. we run it, but we run it on behalf of the European Commission. And that shows you where we've come. So back in the 50s, the Russians were developing this thing called the tokamak. We were developing other concepts. The Russians came out with a publication or with some results. They came over to the UK and they showed some results which said that their machine was producing temperatures which were 10 times hotter than anywhere else in the world. And this was post-World War, a rather suspicious climate. So naturally, everybody was took this with a bit of a pinch of salt and said, well, we failed. Why? What makes us think that this isn't just Russian propaganda? So a group of scientists called the Culham 5 went over, stuck a brand new measurement device using this interesting new technology called a laser. They stuck their lasers on the side of the machines, measured the temperature, and actually they came back and said, yes, you are measuring something that's 10, 15 times hotter than anything else in the world, and that was the tokamak. So it became very obvious very early that the tokamak was the easiest way of keeping this hot fuel inside the machine in a controlled manner. And you really see it. If you look at the history, you start in the 50s and 60s with lots and lots of different devices with lots of different configurations. In the 70s, 80s, and 90s, it really less get built, but then almost all of them are tokamaks. And that's because the tokamak has been shown to be the one that can give you the highest temperatures, that can do the best. So you really see this convergence towards the tokamak, and that's where we are today. So the big machines in the world, most of the big machines in the world are tokamaks, but we do have other concepts. So we've got, like I was saying, we've got the inertial confinement machines. We've got a couple in the UK. The biggest one in the world is in the US. There's an alternative to a tokamak called a stellarator. And a stellarator was an invention that came out of America just after this. I was saying about this Argentinian hoax. Just after that, the stellarator was invented in America in kind of response to this. And stellarators are interesting because, so a tokamak, the way a tokamak works is that you have some magnetic fields that are generated outside of the plasma and some magnetic fields that are generated inside the plasma. And the ones that are generated inside the plasma make it quite hard to deal with, but it makes the machine as in general a bit easier to build. In a stellarator, you say, I'm not going to create any magnetic fields inside my plasma. I'm going to do it all outside the plasma. And that means that the plasma itself can behave in a bit more of a, what's the best way to put it? In a bit more of a stable way. But the machine is phenomenally complicated to build. So complicated that it was only really with the invention of really high performance computing that people could start building these things really efficiently, because they're so hard to design. But there is the biggest stellarator in the world was completed back in 2015, I think, 2014 or 15. And it was called Wendelstein 7X, and it's running in Germany right now, and it's producing some interesting results. So there are other concepts, but none come quite as close to as the tokamak to being actually on the cusp of doing fusion.
You've mentioned a little about some of the challenges, the complexity of the science required and things like that. So what are the key challenges that we face to develop fusion to get to this point of producing more energy than is put in?
Yeah, that's a great question. And it kind of hits the nail on the head, right? Because if fusion is this good, why don't we have it yet? Well, the reason we don't have it yet is because it's extraordinarily challenging. There are a number of challenges. Breaking it down, there is kind of 6 key areas that we need to overcome to make fusion a reality. So, number 1, if I've got this hot fuel, I need to keep it there safely and stably. I need to do that for, I need to be able to do that for half a day, weeks, months at a time. And we can do that. The longest we've ever held one of these hot fuels, the longest we've ever held one of these hot fuels for is a Tokamak in China called East, and that managed to do it for 100 seconds. So that's where we're at the moment. But not only do we need to hold it there, but we need to hold it there in the kind of conditions that can produce a good amount of fusion power. So that's really difficult. That's a non-trivial thing to do, and that's where a lot of the research that gets done on jet at the moment is all about trying to understand how we hold that hot fuel there for a long time. So if we can do that, if we can hold that hot fuel there, and we can do a lot of fusion, we create a lot of heat. Some of that heat we're going to use to power steam turbines, but some of that heat gets it stays inside the plasma, and it's essentially excess heat. And then the question is, well, what do you do with that excess heat? Because it's extraordinarily hot. How do you make sure that you don't damage any of the material surfaces in the machine? Because if I damage my machine, and I mean that I can't run the machine anymore, I can't produce any electricity. So I need to make sure that I don't damage my machine. I need to find good ways of dealing with all of that excess heat. And the other machine that we have at Culham, at UK Atomic Energy Authority, is called MAST. Well, it's actually called MAST Upgrade, which stands for Megaramp Spherical Tokamak. There's a lot to unpick in that title, and I can talk a bit about the spherical tokamak a bit later. But essentially, that machine, one of its headline goals is to try and develop new ways of dealing with this excess heat. So I've got hot, and I've got the cold stuff, and say I can now keep the cold stuff cold. I still have neutrons flying around everywhere, and neutrons do a lot of damage to a lot of things. So they damage materials. So we need to come up with materials that we can build our machine out of that can tolerate all of these neutrons. And that is not an easy thing to do. And it's going to require us creating new materials with new properties that can withstand that kind of environment. Also, if I've got these neutrons flying around everywhere, I don't want humans anywhere near that proximity, right? You or I, we do not want to be standing next to a tokamak when it's in operation. It's not good for our health. So we need to come up with ways of servicing and maintaining and decommissioning the machine that don't require humans or human intervention. So we have to come up with robotics. Robotics is obviously the natural choice to use. And developing those robotic maintenance developing that kind of robotic maintenance is a real challenge, and it's an area where we are really building some expertise now, but we have something to build that expertise on, because Jet, for a long time, Jet has had 2 big giant robots that have been responsible for all of the repairs that need to happen to the inside of the vessel. So now we're at the state where we've got the hot stuff hot, we can keep the cold stuff cold, we can deal with the neutrons, we can repair the machine, but when we're running the machine, we still have to deal with tritium. And I've already said that tritium is not a particularly nice thing to deal with because it's radioactive hydrogen. So we have to come up with ways of dealing with the tritium, and we have to come up with ways of making sure that we breed enough tritium that we can keep the whole thing self-sustaining, because there's no point running the machine if it's just going to fizzle out. Like if we just can't put any more logs on the fire, we can't keep the fusion reaction going. So we need to a self-sustaining machine. So we've got hot stuff hot, we've got cold stuff cold, we've got materials that can handle neutrons, we've got ways of maintaining our machine, and we can deal with all the tritium. That's great, and we can design all of those things, but we don't just have to do that in isolation. We have to design a machine which can do all of that at one time. And that in itself is not an easy thing to do, right? Because it might be that the thing that would be easiest to do with robots is actually the hardest to deal with tritium. Or it might be the materials that we want to use to handle neutrons are not particularly good at handling heat. So we need to use different materials. So we have to come up with a design that does all of these things in an integrated, holistic manner. And those we think are the really big challenges that stand in the path of a commercial fusion reactor. But all of those challenges are areas that we are actively looking at right now. And they're challenges, not impossibilities. So in all of these areas, we're developing innovative solutions right now to try and break through that challenge and come up with something that you can really put into a fusion reactor, put into a fusion power plant, and make a fusion power plant work. But yeah, so they're the kind of key areas at the moment where I think the world is working towards finding solutions.
And those challenges then are also pushing other areas of science beyond just fusion itself, because you have to work in these other areas to support the science of fusion.
Yeah, absolutely. And robotics is a really great example of that, right? So, for example, so I said we've got 2 robots that service jet. These robots have to have sensors on the front of them, because you don't want the robot just going in and hitting a surface or something and doing more damage than it's going to repair. Now, what I should have said is that these robots are all controlled. They're all human controlled, but from humans that are, like hundreds of meters away, using haptic feedback controls. So these humans have to be able to see and feel exactly the environment that they're in, but from hundreds of meters away. So we need extraordinarily sensitive sensors to do that. Now, sensors are used all over the place, and some of the sensor technology that we use in fusion is now finding applications in other areas, like self-driving cars, autonomous vehicles, for example. And there are other examples. So some of the work that went into looking at these removing excess heat, what we call the exhaust part of the machine, is also finding application in things like thrusters and engines, rocket engines. So there are all sorts of areas where we find that actually the technology that you need to do to develop fusion has spin out all over the place. I just need to say the word decommissioning, for example, and all of a sudden you can imagine all of the really interesting application. If we can invent good ways of doing decommissioning, which don't require human intervention, are all safe to do, you can imagine the huge number of applications that those kind of things have. So it's one of those fields where really any kind of investment you put into fusion doesn't just take you further along the path to fusion, but it gives you all of these extra benefits. And people always talk about the Apollo program, the US Apollo program, to get a man on the moon or a human on the moon. And one of the big things about the Apollo program was along the way you had all of these different things that spun out of it, and the same is true for fusion. I mean, not on the Apollo level, of course, we don't get funded like Apollo did, but the same is true. So on the path, it's not just fusion; it's all of the branches that come off of it that start benefiting us in lots of different and exciting ways. And really, we're at the start of that. So as we develop more and more technological solutions for fusion, we're going to find more and more areas where these things spin out. Superconductors is another really good example. So a lot of the superconductor development that goes on in the world at the moment goes on for fusion, but superconductors are really, really high magnetic field materials, have applications all over the place. So yeah, it's a really good sector to work in if you're interested in that kind of innovation space, that kind of innovation ecosystem where basic science starts to breed innovation in all sorts of other areas.
And material science is a big part of that. Obviously, the heat and the cold, the extreme environment you're working with, you need materials that can stand up to those environments.
Yeah, material science is a really, really important area. Developing new materials, understanding how those materials behave is, that is a level of physics that is really in its developmental stage as well. There was recently some of the work that went on at our lab in collaboration with scientists all over the world. So I think a scientist in Japan was the lead author on it, recently looked at how damage in materials actually works and found out that this law of physics that people thought was true, they called the Arrhenius law, were for over 100 years, people thought they understood how materials at cryogenic temperatures, how damage worked in those. And it turns out actually that was wrong. Some interesting quirks of quantum mechanics meant that actually that law of physics is wrong and needs to be revisited. And that, that's a fusion, that's science being done for a very specific reason, understanding fusion, but having this real impact on the real fundamental laws of nature as we understand them. And lots of the stuff in fusion as well has, we do a lot of plasma physics. I'm a plasma physicist. We do a lot of plasma physics, which is very targeted, but also has an impact well beyond the fusion field. A lot of the developments in plasma physics that have been so important in areas like astrophysics and low temperature plasmas and things like that had some of their origins in fusion research.
Yeah, so just in the way that fusion research is driving other areas of science, some are other areas of science fusion is also dependent on. So you mentioned the development of computing as well. So more modern computers with much higher levels of power are essential to the process as well.
I always like to liken this to weather modeling. So everyone knows weather modeling is extraordinarily hard. You only have to, look at the sort of weather predictions that the Met Office come out with on our TVs or something, and you realize just the sheer difficulty in weather modeling, and that takes enormous supercomputers to do. Now, if you remember right at the start of this podcast, we were talking about plasma as the fourth state of matter. Well, gases, weather modeling is all about gases. Gases are essentially plasmas, but with, a third of the complexity or way, way less complexity because all the ions and electrons are combined. So if I'm doing essentially weather modeling, but with plasmas, that becomes phenomenally complicated. And it really takes really, really big supercomputers to be able to chug through those problems and to be able to get the solutions, the predictions that we need to try and understand how our power plants are going to work. So yeah, it's a really complicated thing to do. And it's not just supercomputing either. I mean, some of the components that we're going to want to use in fusion, so I don't know, some of the pipes, for example, how do you weld a pipe that can withstand a fusion environment? Well, we're starting to borrow methods that are being used in other areas of industry, in advanced manufacturing and things like that, to come up with ways that we can create the components that go into our fusion reactors, into our fusion power plants. So fusion can give a lot and fusion takes a lot. It's a really dynamic ecosystem in the research sector, especially so in the UK at the moment. So it's a really, really exciting time in the UK at the moment, where we've got a lot of funding to create this national program of fusion in the UK called STEP, Spherical Tokamak for Energy Production, which is not just at Culham, it's not just at UK Atomic Energy Authority, it's the whole of the nation essentially coming together to find solutions that can create a power plant in the UK by 2040. So it's a really exciting time where all of the knowledge ecosystem that we have in the UK in materials, in technology, in plasmas is all coming together to try and get this goal and get us something which can actually produce electricity.
And the UK is a real world leader in this area, and there's a lot of political backing for it.
Yeah, we're well recognised in the UK as leading the way, and it's largely because of the lab that we have in Culham, where we do. I mentioned all of these challenges, these 6 challenges. We really are the only place on the face of the planet at the moment that actively researches in all of these different areas. So that gives us this world-leading capability. And our government, the UK government, recognise this capability and recognise that it's something that we cannot lose, right? We are at the front of the world in this. We need to stay there because we have the knowledge in the UK, we have the capability in the UK to design the first fusion power plants, but we need that support, that public backing in order to do that. And actually the government have been very, very strong backers of us very recently. We've received about £220 million for a 5-year design project to start to design this first fusion power plant called STEP. So that's the start of the STEP programme. We've also recently received another £180 million to upgrade a lot of the facilities that we have in the UK so that we can, so that not only do we have the the minds, not only do we have the knowledge, but we also have the facilities that we need to be able to drive fusion forwards. So the UK, we have a lot of public backing. We're very lucky that the government recognises the potential of fusion and wants us to be a world leader in fusion. But it's not just in the UK. So there are programs in the US now funding fusion. In particular, the US programs are very good at supporting fusion startups, as are we here. There's a strong public program in China to build fusion, to design a fusion power plant. The ITER project is entirely public funded, and that's from, I said, 90% of the world's economy goes into ITER. So there is a lot of public backing, and I think the reason that there's so much public backing is that there's this recognition that fusion is going to cost, right? It's not going to be cheap, but once it gets there, the solution is so incredibly important to the centuries, millennia afterwards, that we need to have that support now in order to get there.
And obviously there's a lot of politics behind it there. Internationally, lots of different countries working in fusion. How much can difficult international relationships impact on science? I'm thinking, at the minute, issues with China and Hong Kong, and the UK are obviously inviting people from Hong Kong to relocate to the UK. Is that going to have an impact on these international cooperation on fusion?
Yeah, I mean that's a really interesting one, isn't it? About how international politics can affect these sort of things. What I'm somewhat less expert on that than I am on plasma physics, but what I would say is that you only have to look at ITER, right? And ITER has been through quite the journey to get itself off the ground. It was a really non-trivial thing to set up, a really non-trivial thing to get organised, and a really non-trivial thing to even decide where it was going to be located. And the fact that you've got all of these countries involved in ITER who don't get along, right? So China and the US do not get along very well at the moment, but they are both involved in ITER because they recognise that what comes out the end of ITER is going to benefit everyone. And so you get more value by being a partner there than you lose out by not being a partner. And fusion is one of those areas of science where that's really true. You lose out if you're not a partner. So I think that at the moment, we're a little bit, we're lucky to be a bit shielded from a lot of the political ecosystem at the moment.
It's one of the great powers of science that it brings people together across these kinds of boundaries.
Exactly. It's a really collaborative field. You only have to look back at its history in the Cold War era. When our British scientists went across to Russia in the 1960s, that was deep Cold War era. That was a really big statement of sending a UK delegation of scientists over to work collaboratively with the Russians. That's the power that science has, and it's why it's such a beautiful place to work, because especially fusion is a very international field. I have friends all over the world who I've made in this field, and it really sort of the sort of global macro scale politics are something you have to be aware of, but are also something that we are lucky enough to sort of sit outside of a little bit. I mean, there are obvious areas where we get affected, but I think that fusion is kind of beautiful, and science in general is kind of beautiful in that respect.
And then the last thing I wanted to really bring up is commercialization. So obviously it's the challenge to get to the point where the energy in the energy out is greater than the energy in. Then the next stage of that will be making fusion actually commercially viable.
Yeah, that's a good point. I was really hoping you were going to say we wanted to get to energy in greater than energy out, because we've done that. That bit we can do easily. Commercialization. So it's no good if we just build a fusion reactor that produces more energy out than is put in, if it's going to cost hundreds of times more money to do that than any other fuel source on Earth at the time. It's just not worth it, because who's going to buy that? Even with the carbon imperative, even with everything we've just said, money is still king. And who's going to buy a fusion reactor if it's not cost effective? So commercialization and the route to commercialization is really key. And one thing that's really really exciting about the UK concept, so this STEP concept, I said before about spherical tokamaks. So spherical tokamaks, and STEP I should say stands for spherical tokamak for energy production. Spherical tokamaks are, you basically take a regular tokamak, which looks like a donut, and you push it all much more towards the center. So now it looks like a Terry's chocolate orange that someone's poked the core out of. And there's a really good reason for doing this, and that is that one of the three of the most expensive parts of a fusion power plant are going to be the magnets, the buildings, and the cryo plant. So the magnets are are expensive because they are built of superconducting material, which is very expensive to build, very complicated to handle. The buildings are very expensive because they have to be built out of nuclear grade concrete, because you have all these neutrons flying around everywhere. So you need nuclear grade concrete. That's also really expensive. And the cryo plants, cryostats are just expensive anyway, and they have to be big. So if I can shrink my machine, then my magnets get smaller, my buildings get smaller, my cryostat gets smaller. So all of these areas that are the most expensive areas of the machine to build get smaller, so they come down in cost. So all of a sudden now I have a route to building a fusion power plant which is cheaper, and that's what the UK design is working towards. Unfortunately, there's been a lot less research in this area of physics, so that's what we're doing now. That's what the STEP program is all about, is figuring out, can we build this concept design? We think so. Coming up with that concept design and then taking us on the road to building the power plant by 2040. So that's our route to commercialization. But at the same time, there are lots of different private companies now coming up and around. And probably the first fusion power plant will be private, right? Whether we build this STEP, whatever STEP looks like, probably the first fusion power plant will be private, but with strong public backing, because the ecosystem that you're going to need to be able to build any kind of power plant is a private one. You need to be able to do all of the things that private companies have the freedoms to do. And so it's really exciting to see all of these bubbles of private companies now starting to blossom around the place. We have two big ones in the UK, and there are a few in the US as well that are coming up. And so it's going to be exciting to see where the first fusion power plants actually come online from.
So do you want to mention a bit about the companies in the UK?
I can do, yeah. So there are two exciting ones in the UK. There are a fair few fusion companies around the place. There are something, I think at last count there's 40 or 50 around the globe now. The biggest ones, the ones that have opened up the most investment from their funders, there are a few in America, and the ones in the UK, there's Tokamak Energy and First Light Fusion, two really exciting companies that are doing totally different things from each other. So Tokamak Energy, as the name suggests, is based on the tokamak concept. First Light Fusion is based on a totally different concept, something that I think is pretty unique around the world, that I have to say I don't fully understand myself. And it's exciting to see them. It's exciting to see them develop their concepts and running through the sort of prototyping phases that they're going through now. And one thing that's really special in the fusion field around the globe, but in the UK at the moment, is that we're very, very supportive of these private companies, because, well, first off, the more bright minds we have thinking about fusion, the better. So whether they're working for us, whether they're working for in universities, whether they're working for private companies, the more people that are thinking about the problem, the better. But also, I mentioned these challenges. So we have these 6 challenges: hot stuff, keeping stuff cold, materials, robotics, tritium, and integrating all of that. A lot of these challenges are very similar, no matter how you do fusion, right? Almost every way of doing fusion is going to have these neutrons you have to deal with, or have heat. So a lot of the work that gets done and one part of the fusion sector can directly benefit other parts. And there's a very collaborative working. A lot of what we do in the public sector in the UK supports directly these private ventures as well. And so it's a kind of real burgeoning field where what's the term? Competimates, I guess, is the term, where we're all We
Not come
obviously,
across that one.
yeah, obviously we're not competitors with any of the private companies, but yeah, there's this real sort of collaboration, I think, in the field at the moment, which is driving us all forwards.
I think there's a really interesting comparison there where the international cooperation is important, but that cooperation between the public and the private sectors is also really important. The private sector brings that sort of muscle and resources to get into that commercial level.
Absolutely, yeah, absolutely, very true. And then you start thinking about things like how do we design the regulatory environment and things like that for fusion to make sure that it's enabling and not disabling. So there's lots of work to do on that kind of front, but it's exciting to start thinking about that sort of thing. And like I said, the STEP program in the UK, one of the reasons that it's so exciting is that a lot of, I mean, we think STEP will be the first fusion power plant. That's why we're backing STEP. But a lot of the work that's going to go on in that program is going to have such a wide impact on the fusion landscape in general that even if STEP ended up not being the first fusion power plant, the work that happened in the program will have such a direct enabling effect on the whole landscape that it's worthwhile in its own. But having said that, we think STEP is the quickest, best route to a sort of cheap, compact fusion reactor.
And then I guess that's a good place to end. And I don't think I can really do a whole podcast on this without asking you, when do you think we'll actually have fusion up and running where it's providing energy for our households and our cups of tea and everything else?
Well, okay, let's take that in two parts. 2040. The due date for STEP is 2040. So we hope that STEP will be producing electricity by 2040. Whether it's producing enough electricity for you to have a cup of tea from, Lee, I can't tell you that. But we would hope that towards the end of this half of the century, we start seeing fusion electricity put on the grid, and once you've done that, once the ball starts rolling, who knows? By the end of the century, we may all be powered by fusion reactors in our backyards.
Sounds like a really good reason to eat healthy, do some exercise to try to hang on long enough to see it happen.
Absolutely, yeah. Everybody stay around, see fusion.
Nick, when I thought of doing the podcast, this was the very first topic that I wanted to cover. So it's been an absolute pleasure. Thanks very much.
Lee, thank you very much for the invitation. I always love talking about the things that I'm passionate about. And I although I work in the field, I mean, I think even if I worked somewhere very, very differently, I would still feel equally as passionate about this. And I hope that it's been interesting for you and your listeners. And I hope that you'll all go out now and look up all of the exciting stuff that we're doing in fusion, because it's just a wonderful place to work in and a really exciting field. So yeah, thank you very much for this.
Yeah, so tell us where we can find out more about UK AEA and Culham.
We have a website, so ukaea.uk. If you could just type that into Google or something, that should bring you up. We've got social media all over the place at UKAEA official. Search in Google and go wild. Have a look, see what we're doing. Come and visit us when we're not on lockdown anymore. It's a really exciting place, and we do lots of cool stuff. If you come at the right time, you might even see a plasma running through in jet.
Brilliant, Nick. Thanks very much. Good luck with getting that energy out.
Thank you very much.
I hope you've enjoyed this episode. You can find out more about the podcast and upcoming episodes at curiositycake.co.uk and on Twitter at curiosity_cake. Curiosity Cake.